All right, hello everybody. Welcome to EEE 117. This is Dr. Dupes for your class, and today we're going to be talking about more Chapter 10, specifically RMS power today and complex power. So without further ado, let's just go ahead and dive right in. So last time we talked about instantaneous power PQS, power factor, and power triangle, right? This is all very critical component of power theory, just knowing the three different powers. Another thing we're going to do is we're going to compare AC power to DC power. Right now, we all know what the DC system looks like. You have a circuit with just a flat 10-volt source and maybe current flowing through the circuit, which is a flat 5 amps, right? So if you look over here, you're going to have a straight line. This is your current down here and a straight line of voltage. And we know to get power, if we multiply these instantaneous power is P equals V times I. So you can multiply 10 and 5 to 50, but because DC is flat, it's going to be 50 watts all the way across. So you can see I kind of drew it in. There's a lot of area under the curve. So it means there's a lot of energy right here because it's 50 watts constantly. Now, what happens if we take the same 50 and 5 and look at an AC power source? Now, the difference for AC, remember, it goes up and down. You have a positive, negative cycle. So if I say 10 cosine WT for voltage and 5 cosine WT for amps, are we going to get the same power? And I will tell you right now, if you look at it, you can see the AC system. You see the current down here. You see the voltage a little bit bigger. And remember, instantaneous power is P equals V times I. So you have two currents and a voltage and current multiplied together. At the peak, they're going to be all the way up 50 watts. But as you notice, it tend down to zero because that's the sinusoidal wave turned on and then off, on and then off. You're not going to fill up the whole 50 watts. And so naturally, if you multiply all these together, you get these giant humps. And then you fill in the area, and noticeably, there's less area under the curve. So that must mean the average power is not 50 watts. For the DC power, sure it will because it's flat, but AC is going to be lower. And we have a problem, right? And it's going to start getting confusing when we're talking about AC power versus DC power. I don't like that. I don't like being confused and extra wordage and stuff like that. Okay, so here would the real power P be the same as both AC and DC source? No, because AC power momentarily turns off at the zero crossings, so you're gonna have no power then. Okay, versus the DC being constant flat 50 watts. So one thing we strive very hard of in electrical engineering communities is I want to simplify things. I want to say if I have a device that's rated for 100 watts, I want to make sure the voltage I put in for either AC or DC will still give me that same 100 watts. I don't want to have a device and say, well, I have to check AC voltage versus DC voltage. Is there a ratio? Do I need to double check? No, that's too much. Maybe for electrical engineers, we can handle it, but for everyday people using devices, we're going to burn equipment left and right. I'm telling you right now. So a long time ago, we said let's flatten the curve. Let's make everything on one level. I want to have a system where it'll be really nice if I could say I have a 120 volt DC power source, has the same capabilities as a 120 volt AC source. That way I don't have to remember AC needs to be higher or lower and blah, 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 right? It's going to make it so much easier to match parts and select parts out of catalogs. So that's where our goal right now for today is we want to quantify, we want to make rules that if you have an AC source, so you have a voltage across a resistor, this AC source should have the same power and the same voltage output to this bottom resistor with the DC source. So here, remember, power is V squared over R. I want to make sure this AC power, DC power is the same. So these two voltages must be the same as well so that the power can be the same. So this AC source, we want to make sure if DC is 120, this AC source is 120 as well, right? But we already saw with the humps, that's not going to happen. So there's some middle ground we need to figure out here, okay? And that's where we're going to talk about, or what we're going to talk about today. So we got to do a little analysis and math, right? So let's dive in and talk about how do we represent power from AC source. So average power P is always the 1 over T integral 0 to T. So this is the averaging effect of instantaneous power. So P of T is instantaneous. It could be really high 1 millisecond. The next millisecond is 0. It goes all over the place. We don't care about the up and down. I want the flat 1 hour average because that's what I care about, right? Because I'm going to use a device for a whole hour. I want the average power hour. I don't want to sit there and calculate every bumps and dips, okay? So let's go ahead and do that. Let's look at the averaging effect. Well, power, remember, is V squared over R, so you could just say V squared of T over R, right? And where V is just this Vm cosine WT plus theta V, right? And we could make it easier and just assume, let's just take theta V to equal 0, just throw it out. So kind of doing our integral math, we could take the 1 over R out because that's a constant, keep the averaging effect right here, and just square the cosine. So it's Vm squared cosine squared T. Now notice everything in this bracket, this needs to equal the DC voltage because P over 1 over R, that's the same power. So whatever this extra stuff in this bracket, that can be my new AC voltage, which is equivalent to the DC voltage. Okay, so Vm is your actual AC, the maximum of the cosine waveform. I don't really care about that as much. I care more about taking this whole thing and equating this to something called VRMS, right? RMS is root mean square. We'll show you what that means in a second. I want to take VRMS squared over R, and that's equal to AC power. Because then I could take this exact same V over RMS and compare it to DC voltage, and they'll be the same if we have the same power coming out. Okay. So you've probably seen this textbook before. This is a VRMS is equal to square root of 1 over T, 0 to T, so the averaging effect of the squared voltage. Okay. So RMS stands for root mean square. So literally, you take the square root, that's the R, and mean is the averaging effect, and square is squaring the actual value itself. So root mean square, that's where that terminology came from. Now, we could go through all the math if you want, but all that matters at the end of the day is for all sine and cosine waveform, which is typically what we're looking in power systems, take the maximum peak voltage of the cosine function and just divide by square root of 2, and that will give your DC equivalent voltage. It's going to be AC voltage, but it will have the same power level as the equivalent DC source. Okay, so the main thing to take from this is your RMS value of an AC waveform is always the maximum divided by square root of 2. Okay. Now let's go back to our problem here and do a side-by-side comparison. So if my AC voltage, so this AC voltage is 169 volts, cosine of 377T, so 377, 60 hertz, 169 volts is higher than 120, right? The DC voltage down here is 120 volts. So right now you can see I got a much higher AC voltage. But if you take this this maximum, divide by square root of 2, so you have 169 divided by square root of 2, you get 120 volts. So what we just did is we took 169, which is at peak voltage, and say this 169 volts is equivalent to 120 volts DC. Now, technically, obviously, it's an AC waveform, but we have equivalency. So now my new voltage, I could say just 120 volts, and now I could just do V squared over R. That's 100 or 1440 watts. And compared to my DC version, where DC is 120 volts, VDC squared over R, that's 1440 watts as well. So what we did is we literally took this VAC, which is now a RMS value, that is exactly equal to a DC equivalent, and we get the same amount of power. So the beauty of this is now, as long as we use RMS voltages, we can make sure that, or we could do a side-by-side comparison for a DC circuit versus an AC circuit, right? And I'm telling you right now, if you ever go to the back of look at your phone chargers or any equipment in your house, it's going to say 120 volts AC. It means this value right here, your RMS value. not your peak value. If you take a wall socket to your house, you're going to have 169 volts, right? And this is pretty much what we're talking about here. So what's your RMS voltage at your house? So your two plugs on your wall, if you take a multimeter and just a standard multimeter and stick it in the wall, the multimeter does not read peak values. Normally it doesn't. Its default value is always RMS value. Okay. So here, if you plug in a voltmeter and read AC voltage, you'll probably get roughly 120 volts, plus or minus like maybe 5 or 10 volts, depending if you're the night or day. So this is 120 volts RMS. This is AC voltage. But a lot of people like to draw a flat line because this is your DC equivalent. So now, if I plug something in, I don't have to think about, well, how much power is the maximum at the tip of the waveform? How much is different at zero? We don't care about it anymore. We made it all a flat line to make our calculations way easier, right? We don't care about this peak because the peak doesn't happen all the time. We care about the RMS value because this is more constant. This is a more constant what's going on. I like to imagine in my head that when I see a socket on the wall, I don't see these up and down waveforms. I see an RMS value of 120 volts, and I expect that to be constant coming out the socket. Okay. Now, if you do the math, you can look at what's the very top peak right here. This is going to be 169 volts. This is literally actually right here. Where's the peak voltage at your house? Was 169.7 cosine of 377t. So this is your technical formula of a AC voltage. But notice it's 120 square root of 2, because the difference between your RMS value and then your straight up maximum value, your peak value, is that square root of 2 difference. So 169.7 and 120 are two very common voltages you're going to hear in the power system. Okay. Now, question is where can you get this waveform? This is what you need. You need a more specialized equipment called an oscilloscope. An oscilloscope will give you the actual waveform. You have that in your 117 labs. You have this fancy oscilloscope that's like $3,000. A multimeter is like $30 just to show you the difference, right? So you could literally see the waveform, and then you could find the maximum peak value through that, right? But if you don't have an oscilloscope with just a multimeter, it's not going to accurately be able to find this for you. It's only going to tell you 120 volts, okay? Now, we talked about RMS. There's that equation you could technically use for any waveform, but most of the time we just have a couple of common ones we use anyway. These are the common ones you see in power and electrical engineering. The most common one is your sine waveform. This is VRMS is a maximum. For VM is always a maximum, divided by square root of 2. Square root, VRMS, and V maximum are exactly the same. And the reason why is you see this negative half, you're squaring it. So if you square it, it's going to get rid of negative and it's going to be flat and it's going to be flush with the top half. So square waves in terms of DC equivalency is the exact same. Triangle waveform or sawtooth waveforms are triangles. And if you do the math, it's going to be VM divided by square root of 3. Okay. So again, there's typically charts in circuit book that if you see these common waveforms, you need to find RMS values. You could just think of it shorthand. But 90% of the time, you're going to be using this first one, the sine cosine waveform. So just burn it in your brain. AC waveform. If you ever had the peak value, divide by square root of 2 to get the RMS value. Okay. So again, the power industry, most of electrical engineering society, we use RMS voltages and currents for anything in your house because it's simpler that way. So power industry all uses RMS. For this course, you might as well just assume everything I talk about from here on out is going to be RMS values always, unless I explicitly state that it's a peak value. It's just that's how common we use RMS values in today's world. Okay. Now, because we're going to be using RMS, we might want to modify our power and reactive power formulas to represent that, okay? So here you're going to have P is equal to V maximum times V maximum divided by 2. These are your P values. You could split these up and put a square root 2 under each of these, and then convert these to RMS values, right? And there's no coincidence that this works exactly as so, because remember, RMS values are there to make power easier. So the divide by 2 was always there. We just kind of rode with it. So here, the more common power equation you're going to see is a VRMS times IRMS cosine is the angle between voltage and current. Okay. Same thing for reactive power. Split that 2 divided by square root 2 over here. Q equals VRMS, IRMS sine angle V minus angle Y. These are the two much more common ones you're going to use. The divide by 2 versions are only if you get the peak values, which so far, because you haven't learned RMS values, we had to use them. But here on out, we're predominantly going to be using these two new equations with RMS values. And most of the world uses these two. Okay. So lots of talking. Let's start some example problems, kind of see everything working out. So we have a very simple circuit with a load. Now, I don't draw resistors or inductors or capacitors for a load. I call it, it's like a box. So it could be a motor, it could be a light bulb. You don't know. It's a mystery load. So this mystery load is a 4,000 watt load at a power factor of 0.8 lagging. Now, last week, you should know exactly what this means. I want to find a current going through the circuit. I know my voltage. I know my powers. Can I find my current? Yeah, we can do that. So remember, P equals V RMS times I RMS cosine of theta V minus theta I. So my voltage, V, is 120 angle 0 degrees. And notice I said V RMS just to make sure you understand. This is RMS voltages, not peak voltages. So literally, and we know power, that's 4,000. And we got power factor 0.8. So now P is equal to VRMS, IRMS cosine of the angle between voltage and current. This cosine of the angle between voltage and current is also the power factor. You can see right here on the right-hand side. So to figure out just a straight IRMS is you just plug everything in. So you have P for 4,000, V for 120, cosine of angle between voltage and current is 0.8 because that's our power factor. Basic number crunching and arithmetic tells me our current is 20.8 amps. Now remember, if I want to find my current, it's a phasor, so we need both the magnitude and the phase shift. I only got the magnitude. So my I bolded for phasors, my RMS value is 20.8, but we got to find our phase angle. How do we do that? You got to remember, we got to look at the power factor. The power factor would tell us what the angle is because we know the angle of the current of the voltage is 0. So my power factor is 0.8 equals cosine angle between voltage and current, right? We could do the cosine inverse to swap them out. The angle to voltage is 0 degrees, so we just have the negative angle, which is, cosine of -8 on the right-hand side is 36.9 degrees. On the left-hand side, the phase angle of the voltage is 0, so we just have a negative phase angle of the current. Swap the negatives across, and then now you have swap the negatives across and you have 36.9 degrees. Yep. So here, our theta I is negative 36.9 degrees. Also, it's lagging. So because it's lagging, you would know that this should be a negative sign, if you remember from last week. Okay, lagging means that you have a negative, your phase shift for current must be behind the phase shift of voltage. So if you have 0 degrees, this should not be positive, it should be negative. Okay. So that's how you find the current. So just kind of review of power factor and P and Q and S, and also showing how the RMS voltages work out in this now with powers. All right, let's amp it up. So we got the very basic one down with one source. What happens when you have two loads? So first when we did one load, now we have two loads, right? What's a complex power for both the loads, all of them put together, right? So I want to find S. And P and Q for the voltage source. The voltage source is powering two loads. What's my combined powers? What's my P, S, and Q for all this? Well, we got load 1 and load 2, right? Well, remember, the source has to power both of them. So what we can do is we could just find the power for load 1 and the Q for load 1, find a power for load 2 and Q for load 2, and just add them together, right? And then that will be your combined load power together. Unfortunately, you cannot just straight add 4 kW and 8 kVA together and just average these two power factors together. It's not that simple. We actually have to break it down and do math. So Let's do load 1. P equals 4 kW, that's given. Q is 3 kVAR. How do we find Q? That's from our power factor 0.8 lagging. So you go do the math, and then Q will be 3 kVAR. I'm pretty sure we had this. This is actually the a problem from previous last week, I believe. I could be wrong. But do your math. Power factor 0.8 lagging, positive 3 kVAR. Now we got P and Q. Actually, sorry, I'm doing the math right here, right? Cosine of theta is equal. So let's start. P equals 4 kW. That's given. I have power factor 0.8 lagging. So power factor is cosine of theta. So I know my cosine of theta equals P over S. We could swap the S around. So S is equal to P over cosine of theta. Cosine of theta is the power factor. So it's 4K over 0.8. This is 5 kVA. Draw our power triangle out. So P is in the bottom. Here's a phase shift angle, and our hypotenuse is S. So all we need to do is find Q. How do we do that? Well, good old Pythagorean theorem, right? This is basic trigonometry. Q is the square root of S squared minus P squared. Do your math, you get 3 kVAR, right? And this is our power factor is lagging. So because it's lagging, it'll be positive 3 kVAR. Remember, lagging means positive Q, leading means negative Q. So load 1 is 4 kW and 3 kVAR. That's the big numbers we need to take away from this. Now let's do load number 2. Do the same thing all over again. This time I have 8 kVA, right? So these are the answers, but let's go one by one first. So I got a power factor 0.9 lagging. So this time let's start with the power factor. So my theta is equal to cosine inverse is 0.9. So my phase shift between voltage and current is 25.8 degrees. Okay. Now I know my S times cosine of theta will be P. So I could just say 8K times 0.9 equals 7.2 kW. Right? And basically, how do I come up with this? If you don't want to memorize it, draw the power triangle out. Just draw it out every time. Okay. S is always hypotenuse, P is always adjacent. You already have this theta of 25.8. So basic trig, SOHCAHTOA, means we use a cosine to figure out the ratio difference. So power is 7.2 kW. Okay. If you ever do this equation and power is your P down here is more than your S, you flip the variables around. Okay. So we have S, that's 8K. We got P down here, that's 7.2. We got the phase shift. It's very easy to find Q, right? Q is opposite over adjacent, SOHCAHTOA, right? So we got our hypotenuse. Sorry. Sine is opposite over hypotenuse, right? SOHCAHTOA. So we have hypotenuse. We need to find opposite, and we got the theta with the sine function. So Q is equal to S times sine theta. 8K times sine of 25.8 degrees is 3.5 kVAR. This is, remember, it's lagging. We said lagging right here, so this is a positive number. Now we got to just add our powers together. So we got P1 and P2. 4 kW plus 7.2 kW is 11.2 kW. Q total is Q1 plus Q2. So it's 3 kVAR plus 3.5 kVAR. So you have 6.5 kVAR. So P total and Q total, that's both of these put together. We could find our S. S, complex power S, is just the P plus JQ. So we have 11.8 kW plus J 6.5 kVAR. That's our complex power. Okay. So it's a decent amount of work, but as long as you keep this organized, it can flow pretty well. And I mean, this is arithmetic and trig. Just get a pattern, get your quote system that you know how to use power and draw the power triangle, and it's just a rinse and repeat process. Like this type of calculations, I do probably 30% of my entire job is like this type of basic stuff, right? So that being said, we kind of went from 1 load to 2 loads. Now this is where we're going to push you into the deep end a little bit. Let's do 3 loads now. Do the same process that we did before. Find each P and Q per load, right? And then add them all together to find a total complex power. Okay. One thing to show, notice that the L1 and L2 are lagging, but L3, look at, you have negative 4 kVAR, so you're supplying VAR. So this is a leading power factor. So negative kVAR means that you might have to do something different. Instead of, when you add these, you're adding a negative number, so load 3 might lower your overall reactive power Q total. So don't be too scared if you see the number go down. Okay, so let's go ahead and do that, and we'll come back. And let's take a, like what we typically say, 15-minute break. Let's take the 15, maybe 20-minute break. Pause the video right now, and we'll come back and check your answers. So see you in a little bit. Okay, hello, welcome back to EEE 117. We're going to continue with our exercise on calculating complex power for 3 loads. So let's go ahead and see how we did it. So the first one, load 1, we need to figure out the P, real power P and reactive power Q. This is pretty much the same numbers from the first example problem here, but just to go through it, we got real power P, which is 4 kW, and I know it's P because the W stands for watts. That's a hint that it's real power, right? To find, and then we could draw the power triangle. So you have P, S, and Q, and the phase angle between P and S, 90 degrees over here. So just from trigonometry, you know, hypotenuse S is equal P over cosine of theta. Cosine of theta is actually the same as the power factor, which is 0.8 lagging. So 4 kW is 0.8 is 5 kVA. So apparent power S is 5 kVA. From there, we can find reactive power Q just through Pythagoras theorem, where you have Q equals square root of S squared minus P squared. So you just number crunch that. You can get 3 kVAR, and it's lagging. So this is positive. So we get positive 3 kVARs. All right, so we got load 1 done. Load 2 here is 8 kVA, where power factor is 0.9 lagging. So it's very similar to the other problem we did, where we have P equals 7.2 kW. Sorry, we got S equals 8K. So these are the answers. So we need to find power P, draw your power triangle. We have S, we have the theta, right? Theta is a function of 0.9 power factor. We can find P pretty easily. So P equals S times cosine of theta, where cosine of theta is our power factor 0.9. So you know, we crunch that, we get 7.2 kW for the real power. Here, Q is now S times sine of theta. Well, we actually do need to find theta because it's not going to be 0.9 anymore. So we got to do the theta equals cosine inverse of the power factor 0.9, which is 25.8 degrees, right? It is technically positive because it's lagging. And so we have S times sine of theta for Q. That's 8K times sine of 25.8 degrees, which is 3.5 kVAR lagging. So Q equals positive 3.5 kVAR. So we got load 1 and load 2 done. Load 3 is actually already done because I just gave you 4 kW and negative 4 kVARs. But the big trick is the reactive power is negative. So remember, now we have to add all the 3 loads together. Now I'll say this again. You have to add all the P's and all the Q's separately and then combine them to get the actual total complex power. So P total is P1 plus P2 plus P3, which is our total of 15.2 kW. Q total is Q1 plus Q2 plus Q3, or technically it's minus Q3 because it's a negative. You can get 2 kVAR. So you see the third load was supplying VARs, which actually ends up supplying VARs and helping out the first 2 loads, so we get an overall lower reactive power Q. So then my complex power for the whole system is now 15.2 kW plus J2 kVAR, where the actual magnitude of apparent power, if you just put the bars by the magnitude, you get 15 kVA. Okay. And so that's pretty much all the power known for the system. It's very common. You're going to be adding multiple loads together for a combined power. Main reason why is, remember, the power system, all the loads are always in parallel. All voltage sources are in parallel. So think about the whole power system is everything is always parallel with everything. So you're always adding up loads. This could be this could be in your refinery. You could have 3 motors, motor 1, motor 2, motor 3. They're all in the same room. So you have to add them all together to figure out how much power you need to send to the room to power the industrial process to begin with. Okay. So this is a very basic power sizing calculations that you would do if you're a power engineer somewhere, right? Just bread and butter stuff right here. Okay. So just wanted to kind of do a sidebar just to reinforce that complex power. And remember that we're using RMS values as well. So just to rehash everything, you have P is equal to VRMS times IRMS times cosine and angle between voltage and current. These angles don't change just because it's RMS quantities. It's, the phase angle is basically, this is from the source. The phase angle current is based on what the load is. Typically, you have to calculate that. Q is going to be VRMS IRMS times sine of theta, angle between the voltage and current, or sine times the angle between the voltage and the current. The only difference in P and Q is the sine versus cosine. Remember the power triangle, right? Complex power S, just to find the S magnitude alone is V times I. But remember, this is also equal to P plus JQ, where the second part is a complex number. And then you got you got the actual magnitude of S. If you just want to find the magnitude of S, it's the square root of P squared plus Q squared, right? Again, this is just power triangle stuff. Lastly, remember the power factor. That's always cosine angle between the voltage and the current. And remember, within the power factor, there's three possibilities. 99.99% of the time, it's going to be lagging or leading. But by chance, if you get an absolute perfect 1.0 unity power factor, pretty almost non-existent in a real power system, but on paper, you might calculate is that you should call it unity. So technically, 1.0 power factor is not leading or lagging, it's unity. Okay. Now, how else can we use RMS quantities to calculate power? Or remember, for power, it's always dissipated off resistors. So if we have a circuit where you have a load with a part of that load has a resistor, as long as you figure out the current flowing through the resistor, it's easy to find power. Real power is just I squared R. Just make sure this I is an RMS value, not the peak value. That's so very important to quantify RMS itself. So I squared RMS. You can also find power P if the loads are in parallel. So instead of having them in series, if you have them in parallel, it's a little bit trickier to find a current going through the branch because you're going to do a current division. But here, because the voltage is the same across both the loads, we can use the voltage part version of power, which is V squared over R. So this is just another way to find power. Thirdly, if you want to use the power triangle, you can always find real power P from the parent power magnitude times the power factor itself, right? So there's three equations to use, three scenarios. Basically, if you have current and you have stuff in series, use the current version, I squared R. If you have stuff in resistor in parallel you want to look at, the voltage, use V squared over R. And lastly, if you know parent power and power factor, just use that instead, right? So it's just three different tools for three different types of scenarios. Use whichever one is easiest for you, right? Like me personally, I'm much more comfortable thinking in terms of current than voltages. I don't use V squared over R too often. I use I squared R a lot more. That's just my personal preference. And then, of course, the power triangle if we're looking for power. Right, but you do you, whatever you feel safe and feels more comfortable and natural to you, by all means do it. At the end of the day, we all have the same answer, right? I mean, that's the whole trick of circuit analysis. There's always three ways to do every circuit problem, right? It's just a matter of your preference. We could do the same thing for reactive power Q, except remember reactive power Q, this is the reactive power that comes off an inductor, not the resistor. So with RMS quantities, it could really simplify a lot of your calculations. The main thing is we could treat this like a DC circuit where Q is just I squared over X. So instead of I squared over R, it's I squared over X, where X is just the impedance of the inductor. This is why phasors are so good. I don't have to use integrals anymore. Power is very simple. I mean, this is just multiplication and exponential, right? Same idea with Q. If you know the voltage across an inductor, you could just say it's V squared over X. Very common that we use this when calculating reactive power Q. Lastly, you can find Q either through trigonometry. So typically here, if we know power and the phase angle between the voltage and current, we could actually find Q itself. Now, normally you can find Q from S times sine of theta. That's pretty common. But I wanted to throw a little extra part here because you might not have seen this before. But this is just basic trick, right? So again, power triangle, draw it every single time. You got that angle. You got the 90-degree angle, then you got the angle that you're looking at. You got power P and Q. P is adjacent, Q is opposite. SOHCAHTOA, TOA is tangent is opposite over adjacent, right? So then you just swap things, take adjacent, swap it around, and then you got Q equals P times tangent of theta. Okay. So honestly, this is a pretty rare equation to use, but I just want to point it out to you. It's an extra option you can use, right? So I'm a visual person. I think most people are. Drawing the power triangle will kind of help you know what equations you could use to find P or Q or S given what you're given, right? Okay. So just a summary of everything we talked about today. So the big picture stuff, especially for power engineering, is for sinusoidal currents and voltages. I wrote voltage, but it could be for current as well. The RMS value is always the magnitude, the peak value divided by square root 2. Always. So just burn in your brain, divide by square root 2. Okay. Real power P is V times VRMS times IRMS cosine the angle between voltage and current. Q is VRMS times IRMS times sine angle between voltage and current. The magnitude of S can always be just the raw V times VRMS times IRMS, just the two numbers multiplied together. Complex power S is going to be with real power P plus J reactive power Q. Again, some people like to call Q imaginary power because it is the imaginary component of your complex power, right? Because complex power always has real plus J imaginary. I like to use reactive power, but don't be so shocked if somebody calls this imaginary power as well. Okay, so P plus JQ. This is the bread and butter basics of where power triangle comes from. Okay, and also don't forget when you have loads in parallel, you can add individual powers up to get a combined total. Right, that's typically, I mean, that's very common in a power system. And just to show you the numbers, that's all the exercises we did today. Okay, that's pretty much all I have for today. We're going to come back next time and talk about optimizing loads, power loads, and just, more tools in your system that you can use to analyze and make power systems more efficient and just get the road ready to become that power engineer you want to be. Okay. So thank you for showing up. I hope you guys have a good week, and we'll catch you next time on the next session. So you guys have a good day.